so we're back to look at conditional probability, and what we want to look at now are some of the formulae that can be useful when you're working both with conditional probability and set notation. Some formulae that might be shortcuts to the working out you're trying to do. So, first formula I want to introduce you to is the addition formula. This says that the probability of the intersection of two sets is the probability of one added to the other, and then the union of the two subtracted. Now, we've actually been using this implicitly, we've come across problems before where we're adding together two sets and we seem to have too much. The probability is too high, or the frequency is too high for what we were expecting. So let's have a look at this scenario. In a class of 20 students, we did a little quick survey. 14 say they have an Instagram account and 10 say that they have a Twitter account. And every student in the room did say they had an account. Well, there seems to be too many responses. 24 responses from a class of 20. There's 4 too many responses. And we reasoned before that these 4 extra responses have come because some people responded twice. Some people put their hand up to say I have an Instagram account, and they also put their hand up to say they had a Twitter account. So we reasoned that those students are the ones in the intersection, and then we could draw our Venn diagram and solve some problems working on from there. So let's just add this to the Venn diagram. There were 0 students who didn't have any of the accounts. 4 students had both. And to complete the Venn diagram, we'll use our subtraction to say there's an additional 10 for the Instagram and there's an additional 6 for the Twitter. So this is how we worked on those problems where there seemed to be too many or too much. There seemed to be an excess. Well, we're actually using this formula which works with probabilities and also with frequencies like we have here. We've added together the frequency for the Instagram account, 14, with the frequency for the Twitter account, 10. We got 24, and then we subtracted the union. We subtracted the number of students in the class. 14 plus 10 subtract the 20. And that gave us 4, which is the intersection. So like I said, we've been using this informally up to now, but would like to formalize its use. Okay, looking at this formula, we can actually deduce a second one by rearranging to make the union the subject of the equation, or the union the subject of the formula. So here's a second variation that can once again be useful. Let's see if we can get an algebraic justification for why this works, just to convince ourselves. Let's construct a Venn diagram with these probabilities. Probability of A is A, probability of B is B, and the probability of the intersection, we'll call that I. To construct this Venn diagram, we're going to start with the intersection, which is I, and then we'll use a subtraction technique to fill in the rest of the Venn diagram. So the probability of A is A, so the rest of A should be A minus I. If we add these together, we get the A we're expecting. Similarly, we'll get B minus I on this side. Okay, can we find an expression for the union? The union is going to be all of these 3 regions added together. So, A union B equals A minus I plus an I plus B minus I. Simplifying that, we get A plus B plus I. And here's the nice bit. Let's substitute those probability expressions back in. So A was probability of A, B was probability of B, and I was the intersection. So from that, we get our formula. While we're thinking about it, if we had mutually exclusive events, this formula would be slightly different. In fact, it would be the same. The intersection would be 0, so the intersection is redundant. And we could think to ourselves, for mutually exclusive events, the union is going to be the probability of A plus the probability of B. There's no overlap. These two events cannot occur at the same time, so we don't need to consider the intersection. There's no problem if you do, you'll just have a 0 or a subtract 0 in your calculation, but ahead of time, you can be aware that the union is just going to be the two probabilities added together. So these two addition formulae, massively important, massively useful when it comes to solving some complex set notation Venn diagram questions. Okay, let's just see them in action. So probability of A, probability of B, and we're given the union. Asked to find the intersection. I'll start with the version on the left-hand side. This is the one that you're given in the formula booklet. I'll just substitute the values that I know, either that I've been given in the question or I'd already worked out up to this point. And it's just a nice bit of rearranging from here. And that gets us an answer that the intersection must be 0.4. Now, obviously, we could have just started with the formula on the right-hand side, with the intersection being the subject, which would have been just a little bit more straightforward. For some reason, they only give you one of these in the formula book for the exam, and you'd have to deduce the other. I say you'd have to deduce, I would actually expect you to have memorized these. You would have done so much practice by then, it would be impossible for you to not to have memorized them. Okay, let's come back to this situation. See if we can find another formula. So, if we were looking for the probability of A given B, we know that we're initially interested in only set B. And from there, we want to know how much of that region is actually within set A. So, in this case, the denominator is going to be B minus I plus the I, and the numerator, the section, the region of that is within set A is just I. We can tidy that up a bit with some simplifying, and we just get I over B. Okay, let's do the same as we did before. We'll substitute back in the probability statements, and we see that we get intersection of A and B over B. Okay, this is one of my favorite formulas. I really like this one. I'm always careful that I get the intersection in the same order as the given probability. So A was first in the given statement, so A is first in the intersection. B second in the given statement, B second in the intersection. And it's the intersection of both divided by the probability of the second one. The intersection of both divided by the probability of the last one. So if you keep the format, the syntax in that same orientation, you avoid making any errors or mistakes with your working out. Okay, so these three formulas we should be able to work with. You can do some rearranging. If we were to rearrange, trying to make the probability of A intersection B the subject, this is what the given formula, that's what I'll refer to it as, looks like in the formula booklet. Not the most intuitive rearrangement, but as I said before, you will have these memorized long before exam time. Okay, let's see this one in action. We're given events C and D, and we know the probability of C, D, and the probability of C given D. And we're asked to find the intersection of C and D. Okay, as soon as I know I'm working with a given statement, I like to write out that given formula straight away. So it's probability of A given B equals the intersection over the probability of B. I'm going to switch these out for C and D in the correct places. So the probability of C given D is the intersection of C and D over the probability of D. I'm going to substitute into here and then rearrange afterwards. So the two probabilities that we know can go straight in, a quick rearrangement, and we know 0.3 times 0.6 is going to give us 0.18 for that intersection. Once again, we're here working with a given statement, D given C. I'm going to write out the formula, put the correct variables in their place, so I get probability of D given C is the intersection of D and C over the probability of C. Okay, Be careful, some students, they just really go into autopilot and put these in alphabetical order, where C comes first and then D comes second, and then they end up dividing by the probability of D, which is why I want you to get into the habit of keeping the syntax, keeping the positions of each of these variables, of each of these events consistent. Okay, substitute what we know, 0.18 over 0.2, and that simplifies down to 0.09. Right, and lastly, here we're just asked to find the union. Well, I already know a couple of givens. I know the intersection, and I know the probability of C and D, so this goes back to one of the original addition formulae, and I'll just substitute into it. That gives us 0.62. So these three formulae, we want to make sure that we can use them to work with situations involving set notation, probabilities, and often Venn diagrams. Let's have a look at a couple more examples. Here, given that y equals 0.6 and the intersection of x and y is 0.4, can we find not x given y? This is going to be a little bit tricky. The very first thing I'd want to write down here is the probability of not x intersection y over the probability of y. Now, I could go ahead and substitute, except I don't know the numerator. I don't know the probability of not x intersection y. I've not been asked to produce a Venn diagram, but it will be massively useful for me to get going. So, Venn diagram, starting with the intersection, then I can add the rest of y, and I don't actually have any more information. So it's an incomplete Venn diagram, but it was necessary to go ahead and complete this question. The intersection of not x and y, I now know is 0.2. 0.2 over 0.6 cancels down nicely. Okay, let's look at another one where we would need a Venn diagram to be able to move forward with the question. So, as soon as I see that given statement, I like to write the intersection of B and not A all over the probability of not A. Probability of not A, I do know that straight away. It's going to be 1 minus probability of A, 0.5. But the intersection of B and not A, I'm going to want a Venn diagram to know exactly what that is. Okay, we'll start with the intersection we're given, 0.4. Probability of A is 0.5, so that leaves 0.1 on the outside. The probability of B is 0.5, that leaves 0.1 on the outside. And the probability of A is also 0.5, leaving 0.1 on the outside. And on the outside of both sets would have 0.4. So I've got a complete Venn diagram this time. I know that I know all of the intersections, regions, probabilities I might need to use. B intersection not A is 0.1. So 0.1 over 0.5, nice and easy. So to summarize, here are the formulae that we've come across. In general, we have our given formula. We have 2 addition formulae for the union and the intersection. For mutually exclusive events, because we know the intersection equals 0, the addition formula for the union is shortened to just the probability of A plus the probability of B. That can come from your contextual knowledge of what mutually exclusive actually means. And for our independent events, we do know the intersection of 2 events is going to be the probability of one event multiplied by the probability of the other. And similarly, the probability of A given B is going to be the same as the probability of A. Since they're independent, it doesn't matter that B happened first, the probability of A is constant. The probability of A is unaffected by the fact event B happened prior. So, this is a summary of the formulas and some of the contextual understanding you'll need to successfully solve the sorts of problems you'll encounter with conditional probability, set notation, and Venn diagrams.